Hi, in this video, we'll be using the Epic Scan application to collect an X-ray fluorescence map on a sample. This is a primary and main data collection mode for the X-ray Microprobe beamline at GSE cars. Hi, I'm Matt Newville, one of the beamline scientists at the GSE cars Microprobe, and this is part of the training videos for getting you to use the X-ray Microprobe well. So now that we have a sample in the beam and we can see the X-ray fluorescence spectra, we'll want to collect an X-ray fluorescence map on that sample. So again, the field of view here is a square millimeter. And the beam size is typically a couple of microns. In fact, it's a couple of microns now. So we'll use this Epic Scan application to set up and run an X-ray fluorescence map. What we'll do is we'll use, as shown in an earlier video, we'll use the fine stages on the sample stage to raster the sample through the beam. So we'll effectively be moving these stages here, and at each point collecting the full spectrum X-ray fluorescence spectrum at each pixel on the map. We'll do it really fast. We'll use a dwell time that's below 50 milliseconds per pixel, and we'll continuously scan in the X direction and then step and go back in the other direction in Y. To do that, we'll use the X-ray or the Epic Scan application, which when first brought up has some settings. So here is a username and proposal number and so on. Here, we're working in the demo folder. So I'm going to click on the tab for map scans. There's also tabs for XF scans and for linear scans and for using commands and macros that I'll show you in a later video. Right now we want to do just a map, and we want to use the fine X and fine Y stages. There are other stages that we could use for the inner loop. We can use either X or theta if a rotation stage is hooked up for tomography mode. And for the outer loop, we can use other stages, but we typically use fine Y as the stage to use for rastering the sample back and forth. We'll set up, again, since the fine stages are centered at 0, we'll make a map that's centered at 0 by going plus or minus in some increment. So we'll start with doing maybe a 500 micron square map. So here you can select known sizes of maps just to make it easier to set up. I'll select 500 by 500, but I think we won't want to do 2 micron steps just in the interest of time. I'll make this a 5 micron step map, and I'll make that a 1 millimeter map, but at 5 by 5 in 5 micron steps. And I'll also make that go not at 50 milliseconds, which is pretty slow for us. I'll make it go at 20 milliseconds, which is more of a typical scan. So that way we can do this map during most of this video. So now this is set up. That's basically the entire setup. I'm going to save these settings. I'm just going to save that by going Scan, Save Scan Definition, and I'll give it a name. I'm just going to call this 1 millimeter map. I'm sure that we have that defined already. So if I hit return, it'll say, do I want to overwrite that? Yes. That just helps me remember what the settings were, but also we would be able to use that 1 millimeter map name for this set of parameters, moving the stages in this way and collecting for that time in a macro and say move to this point and do that map. So I'm just going to then give this a file name. So this is Garnet. This is a Garnet sample. I won't talk about this sample in much detail at all. I'm just going to call it Garnet map, and I'm going to hit start. This will start the map. In fact, if we go up, it says preparing, running pre-scan routines. I'm going to go up to the intensity view here, and you can see that the intensity in I0, the ion chamber, and also upstream, did a bit of a dance as the piezo crystals for the monochromator were tweaked just to make sure that everything was going well. And now you can see the fluorescence spectrum collecting, and you can even see some changes in it. And you can see the sample going back and forth along in the beam, and on the microscope field of view, you can see that we're rastering that sample in the beam. The lag for the video over the real VNC is a little slow, but you can see that it's rastering well. Now to view the data, you can also see we're going to do 200 by 200 rows and 200 columns in that map. It's already on row 9. So to view this data as it's coming in, I'm going to select GSE MapViewer. That will run this program. This program does a few things. First of all, the main thing is that it allows you to visualize the map data. I'm going to pick that we're working in the demo folder, and then under demo there's a maps. So I'm going to just select that. There, you can already see that there's a Garnet map, raw map data folder, but I'm going to select this top level maps folder. That's where we're going to be working. Each map that's done, so this application does two things. First of all, it helps you visualize the map data, but at the beamline it also constructs the full map. So as you can see, as the data is being collected, there's a raw map folder. In that folder is a bunch of files from the different sources of data, from the X-ray fluorescence spectra, from the electronics from the X-ray fluorescence detector, from the motor controller, and from the ion chambers also, and extra data that's collected, ancillary data that's collected. But I'm going to select this one file that will then be constructed. Right now it's a kilobyte, but it'll get much bigger than that as we open it. And now we'll start processing the data. You can see it's processing row 3, 4, 5. It takes a little bit of time to process the data, but not as much as typically not as much as it takes to collect the data. Once this is set and we've gone through 24 rows, now we can select what we're going to make a map of. So we will make a single ROI map, and we will make a map of, say, iron. That will be pretty dull for this sample, I think, but we can click on this and show a new map. There's the intensity of iron in this sample. So you can see some bounding. Actually, I think this part over here, if I go over, now that you see on the left, there's sort of a band that's going up into the left, and that's this part. I think there's just no, that's just not very interesting for the sample. That must be the backing glass that this is on, or the backing quartz. And the sample's still rastering back and forth. So while that's going, there's a few things you can do. You can, for the intensity of, say, iron, you can change the color table for any one element that's shown. There's blue to red. And you can also change the levels, where the highest peak is, where the highest intensity is, and where the lowest intensity is. We tend to leave this in auto contrast mode, which makes a histogram and then builds the intensity so that the top 5% and the bottom 5% are shunted to 1 and 0, and that tends to remove the most egregious outliers and points that are definitely dominating the intensity. That's by default. You can play with that, and you can play with the intensities all you want, and you can play with the different colors. Often, the ones near the top are the most, actually the known to be most useful, or in our opinion are the most useful. So either gray or one of these few near the top, cool, warm, inferno, and so on. These ones down at the bottom are sometimes fun to play with, but you can play with them all you want. There's other things you can do with this image of the data. You can flip it, so you can rotate it and so on. This map in the normal view, in the flip row, if I reset the view, this is going to be the same orientation as the optical image of the map. So really that it starts in the lower left-hand corner. The lower left-hand corner is the lower left-hand corner of the sample. That really is correct for all your maps. You can also click on a point and we'll show you the pixel numbers and the intensities and the positions of the X and Y motors. And I'll come back to that in a second. But now, like I said, the data is being collected, and here we're only showing 28 rows. So this application can also continue processing the data. So I'm going to click on Add More Rows. It will process up to 100 more rows. It's sometimes useful to limit how many it actually processes so that you can look at the data before it gets too far along. And since it takes close to a second, you're waiting a minute or more. And so if it's a huge map, you may want to limit it and say, let's just take a look at the map before we finish processing it. Anyway, that's done. So now I can hit Replace Last Map, and now it's built more rows, and it's built them up on the top. As it starts in the lower left and rasters back and forth, the job of this program is to undo that back and forth and construct the full maps. We can also look at other elements in the map. So if I make, if I look at not only iron, but say in this sample where zirconium is interesting, because this sample will have many zircons, so these high intensity. In fact, you can see with the auto contrast level, if I make that none, you see these very bright points. Those are zircons in this garnet sample. And if I increase the contrast level, those will pull up and you can see other lower thresholds, lower intensity things below them. Also in this sample, the yttrium is kind of interesting. It tends to be banded. So there is yttrium in this garnet. We can also see other elements as well. So I think that like arsenic shows up as being in this backing glass. I think it's on glass, not on clean quartz. And so one thing we would want to do is show a 3-color map. So put one color, red in one for one ROI, green for another, and blue for a third ROI, so that we can see 3 ROIs at once. So I'll look at those iron, yttrium, and zirconium here and replace that. And now we have a different map that shows red in 3 colors, which shows red for iron and red, green and the yellow is showing yttrium, and then the zirconium is blue. So these zircons are showing up in blue. And again, the contrast level is set. So if I click none for the contrast level, it's difficult to see the yttrium. There must be some point that's very high yttrium that's swamping the rest of the counts. But the zirconiums are saturating at a few very small pixels, like there's a zircon. So you can zoom in on this just by clicking the left button down and dragging and circling in. And you can also say, let's try to get the spectrum just for those small number of pixels. Here I can say, select the pick area for XRF spectrum and just draw a little blob around that. And this will bring up the same sort of data viewer we saw for the X-ray fluorescence spectrum, and here's where the zirconium is. So that's a little zircon right there. We also see iron. The iron is ubiquitous in the sample as a garnet. And so that's a very high level of zirconium. In fact, if we click on the ROI for zirconium here, we can get the counts. This will now be, that's saying that there's 4.8 million counts per second of zirconium in those 9 pixels. That was 0.18 seconds, and there's 4.8 million counts per second of zirconium. That's summed in the 7 detectors together. I can put this away. I'll move this over here. Actually, so as you can see, since we're using one screen, it can be confusing and complicated to find all the screens. So I'll right-click on this image and zoom all the way out, and we'll get back to this image view, and I'll go back to this change the contrast level back to a reasonable level of intensity. And let's go look at let me zoom in here and look at this yttrium section. Again, I'll pick area for XRF spectrum on the map, and I will draw a blob here. And is that yttrium? Here is where you would be asking yourself, is that yttrium real, or is some other effect going on? So here's the spectrum for those points. That's 2.4 second integration, and we see zirconium here. So there's still zirconium everywhere, and that is yttrium. That looks like a real peak. You might ask yourself, and maybe the point of this experiment would be, well, what's the yttrium doing, and what's its chemical form? And so we could answer that question by doing Zanes, and we'll do that in the next video. Here we're seeing 200,000 counts per second of yttrium in that area in the all 7 detectors together. So I'll put this back over here. We're still rastering back and forth, and you might want to know how far along are we. So I'll go back to our data collection window. It's challenging to find all the windows when they overlap, and this says it's at row 126 of 200. So we're almost done with this map. I'm going to go back to here to the processing and add more rows. We're only on row 62 and we have 60 more to go. So while that's building up, let me also zoom this out and say that zoom all the way out. Again, you can like do things like save the image. You can show XY slices. So if I say show a horizontal slice and I click on this, that'll show a horizontal slice of those different elements through that. You can do a vertical slice and so on. There's several things you can do with this. You could basically browse through the menus. You can rotate, you can play with the smoothing, you can add a scale bar and so on to this image. I should say the map also shows information about the map. So here is the pixel size and so on in the map. And then also there's a map areas. So we already drew 2 little areas on the map. If I show map area 2 on the map, that remembers that it drew that map, and it will refine that XRF spectrum. If I click on that, it'll go and find that again for that little area that we defined. And also from this map, I can select and save points. So if I want to do, next thing we might want to do with this map is say, I would like to measure the yttrium zanes at this point. So if I click on this point here, I'm just going to click there. I'm going to get rid of that and say, show no slices. But if I click on a point, this point here, and just give it a name. So I'll call this Garnet spot 1. Spot 1. And hit return. It draws a little diamond there for that 1 pixel that's shown. That pixel there is shown. That's saved in the map. If I now go to this map areas and select the areas, that will show up. Garnet spot 1 is there. And if I clear the map of all the areas and show that on the map, that shows up there. That's where that spot was. These are the pixel numbers for it. But also in our list of positions in the sample stage itself, that position now has been written to this as well. So we can move there and go to that position and do some more analyses. So we'll use that as a main way of using the map, so that you can make a map, select several points. I'll save another point here. I'll just click there and call that spot 2. And hit return, and maybe this one and call it spot 3. And again, those get saved in the map file with the coordinates, and they get written to the sample position list. Now that we've built more rows, we can see a bigger map. There's even more, there's a whole band of yttrium here. So we can zoom in. Let's save another point. Let's call this one spot 4. And it's fine to save the positions as the map is being collected and built. They will be preserved. And we might be able to add more rows to the data as we're getting close to done with this. And then the next thing we'll want to do, I think, is to go and do the yttrium zanes at some of these points here. And again, if I go to map areas and we have a number of points, say if I click on spot 3, show the XRF spectra for that 1 point. That's the spectra at that 1 pixel for the yttrium, where the yttrium spot was. If I click on yttrium, that shows that there's 200,000 counts per second of yttrium in that 1 pixel, that 20 millisecond spectrum. So with that many counts, with more than a few thousand counts, we can measure the zanes spectrum quite easily on the microprobe. So we'll do that next as we're building this up. This map is almost complete anyway, so I might add more rows and replace this map. And I think that shows you how you can work with mapping data. Actually, that shows a nice effect that as the map was still being built, it added some blank rows before it filled it in, but once it's done, it'll replace those so it has a complete data set, and then it won't be contrast limited. We can wait until this data collection is done for this video, but there's this nice band of yttrium, and I think the next thing we'll want to do with this map is do the yttrium zanes on this. So again, this shows you how to use the GSE map data collection. We started it. Just as a reminder, we defined and wrote a map, scan parameters, and we ran a map. It was very easy to do. We read the map in with the map viewer and built these images that we can then use for the data collection. So I think that's a good start for doing mapping. And in the next video, we'll talk about how to do Zane's scans from using the points from that map, and then how to write a whole slew of a sequence of spectra data collection with that map. So thanks, and hope to see you in the next video.